So welcome students to this second part of Sturm-Liouville problem, and in this part we are going to continue our study of Sturm-Liouville problem. So let us write down the problem which we have in our hand: pxy prime whole prime, okay, plus qxy plus lambda rxy equals to 0, right? That's the problem which you have. And here, what is the assumption here? You see, p, q and r are smooth, okay, smooth, that is differentiable, continuously differentiable with p and r positive. This is what our assumption is in the interval I, which is alpha beta. Okay, now lambda is given to be the parameter, right? That's just a given quantity, you don't have to worry about it. And the question is, the initial data is there, the boundary data, and the boundary data, okay, what is the boundary data? The boundary data is a naught y at the point alpha plus a1 y prime at the point alpha equals to a, let's say, and I have assumed d naught, right? Y at the point beta plus d1, I think, yes, this is what we used actually from the last lecture. Beta y prime at the point beta. This is because this is, let's say, maybe I can take a equals to, yeah, I think I can take that. It is better to do that. Let's take 0 0. I think it is better to do 0 0. Let's do it for this. So boundary data, this is given to us, right? That's the boundary data which we are working with right now. Okay. So the problem is called, so again, let's just call the whole thing as star, and this is called a regular Sturm-Liouville boundary value problem. We will denote it like this. Okay. Now, what did we learned two different properties of the eigenvalues, okay, and eigenvectors, and the third property now we will start here. So theorem 3. So what is the third property? Third property says that if for a regular Sturm-Liouville boundary value problem, star, let's say, star, okay, eigenvalues are real. Yes, is it okay? So basically what it is saying is this. See, if you remember the first in the last video we talked about one example, and in that example we definitely do not require, we did not calculate what happens when eigenvalues are complex, right? Of course we could have done, but we did not. Okay, so the thing is, we said that they are real, so you don't have to worry about complex, but why are they real? This is the theorem which actually shows that they are going to be real. Okay, so proof. See, if they are not real, let's start with complex eigenvalues. Lambda equals to a plus ib, let's say, okay, be the complex eigenvalue of star, eigenvalue of, and what is the corresponding eigenfunction? Let's just call it phi of x, and what is it? It is some function mu x plus I gamma x, let's just say gamma x, okay, be the corresponding eigenfunction of star, of course, corresponding eigenfunction of star. Is it okay? Yes. Okay, so then what do you have? So this lambda and that phi is going to satisfy the equation, right? Okay, so what does it mean? It means px times mu x plus I, let me put it in a second bracket, I mu x, derivative of that, right? I think I am missing another derivative here, derivative of this, okay, plus qx mu x plus I gamma x, okay, plus A plus IB lambda Rx, okay, and then mu plus I gamma. This is equals to 0. Is it okay? Now, if you have something like this, you see, we can actually break it up into real and imaginary parts, right? And we can write, and what we will have is this, the linear L of mu plus A mu of x minus b gamma of x. Okay, this I want you guys to check yourself, huh? Please do that. L, and what is L mu and L gamma, right? L gamma plus b mu x minus plus a, sorry, gamma x here, a gamma x times r of x equals to 0. And where, what is L? L, as we have talked about in the last video also, L of y is p y prime whole prime plus q y. That's your L. Yeah. Okay. So these two is possible. So please check this part. Check. Okay. Now, what happens is, once this is clearly true, there is the boundary data also, and the boundary data, let's look at the boundary data. The boundary data is a naught times, again, that also you can break it up. So it is mu of alpha plus a1 mu prime of alpha is 0. Yes, and again a naught gamma of alpha plus a1 gamma prime of alpha is 0. So breaking it into real and imaginary parts, that is, and simultaneously it is d naught mu at the point beta plus d1 mu prime at the point beta is 0, and here you have d naught, sorry, gamma at the point beta plus d1 gamma prime at the point beta is going to be 0. Is it okay? So those two conditions are fine. Now you see, you remembered we did that Lagrange identity, right? Exactly the same Lagrange identity, we are going to use it here. So what we are going to do is this. Now note that if you have mu times L of, gamma times L of mu minus mu times L of gamma. Yes, you remember we computed something like this, right? This is the Lagrange identity part, that exact same. If you do write it, then it will become alpha to beta. You see, L of mu, you know what is it? See, L of mu is minus a times mu plus b times gamma times r, right? And similarly, A of gamma is also like this. So we can just put it here. So what we are going to do is, I am going to write it like this, minus a mu. I am not going to write as a function of x, so that is always given, right? Minus b gamma times gamma r of x. Okay, forget about writing x. Let's not write x. Plus you have b mu plus a gamma, okay, and then mu times r dx. This is what you have. Okay, I'm just calculating, I'm just putting L of mu and L of gamma from here. Yes, I'm just putting it here. That's all. I'm not doing anything. Now, if we just compute it, it is alpha to beta. You see, basically mu and gamma, that part is gone, right? So basically, we are left out with b times gamma square plus mu square, okay, r dx. This is what we have. Yeah. Now, if you just calculate it, it is basically nothing but p of x mu, gamma mu prime, gamma mu prime minus mu gamma prime, okay, from alpha to beta. Is it okay? And that is going to be 0. Yes. Why is it true? Can you guess why it is true? See, what is happening is this. These from here to here, it is fine, right? It's just a calculation. Where am I getting from here to here? How am I getting it? I know by Lagrange identity, this is equals to p times the Wronskian, right? This we talked about in the last video also, exact same thing. Or you can go back to the week 9 second video most probably. Then also you can see the Lagrange identity, we get it there. So basically this is equals to this from Lagrange. Okay. So once that is true, then what we can say is, the thing is, Now, if you calculate this thing, gamma mu prime minus mu gamma prime from alpha to beta, because of this initial data, okay, sorry, the boundary data, if you can just check the boundary data if we just put it here. Why this is true? Because in the boundary data, since a naught square plus a1 square is not 0 and d naught square plus d1 square not equals to 0, so the basically the corresponding the coefficient matrix that is going to be singular, and from there you can actually calculate this part that this is going to be 0. This is exactly the same thing we did in the earlier video, so I'm not going to explain it anymore. That's fine. Okay, so that is there. Now if this is 0, then what does it say? See, it says that this particular thing is 0, right? That's what it is saying. See, I should have write it like this. Here I should have write it as p of x gamma mu prime minus mu gamma prime, you evaluated between alpha and beta is this, right? And then, so basically if you do that, then you see this is nothing but 0. So basically that means b times integral a to b gamma square plus mu square d r times dx is going to be 0. What does that imply? That will of course imply that b is 0. Why? Because see, gamma square plus mu square, gamma and mu are the real and the imaginary part of phi, right? Yes? See, since gamma and mu are real and imaginary part of phi, and what is phi? Phi is a non-trivial solution, and phi is non-trivial. Okay, so you see, gamma and mu are not simultaneously 0. It cannot be both 0 at the same time. So basically mu square plus gamma square cannot be 0. Yes, at least something has to be there, positive. And then what happens is, if you are taking r is always given to be positive. So between alpha and beta, that particular term is always positive. So beta times a positive term is 0. That implies beta b is 0, right? Okay. If b is 0, therefore lambda has to be equals to a, which is in r. Is it okay? So if it has, so basically what it says is this: if for a regular sturm Liouville boundary value problem, the eigenvalues are always going to be real. Is it okay? Right. Now let's look at our theorem, and this is very, very important theorem. The thing is this, we are not going to prove, I'm not going to prove this theorem for this course. The proof is little complicated, okay? What the thing is this, why, and it is, it is very lengthy actually, yes? If you are interested in looking at the proof, please, so for the proof, let me put it this way, for the proof of the following theorem, one may look at the book, the Coddington-Levinson book, Coddington book, Coddington OD book. Okay, it is there. It is very explicitly written, very detailed written. Okay, so you can go through that if you want. But for this course, I'm not going to do it. I'm going to explain the theorem for you. Okay, theorem, and this is very, very important theorem. Yes. Okay. So what is it? So let me put a star here, double star. Very important. Okay. Okay. What does the theorem say? It basically says, see, the thing is this. Let's say, if I give you a problem, you can solve the problem, let's say, and then you can find what are the eigenvalues and eigenvectors. What is the guarantee? That given any regular sturm Liouville boundary value problem, there exists, yes, there exists a, this thing, eigenvalues. How do you know there are eigenvalues? And after that also, if there are eigenvalues, how many eigenvalues are there? How are we going to guarantee that? Okay, so what we have is this. For a regular sturm Liouville boundary value problem. Is it okay? Which one? Star. Star. The problem which we are talking about. There exists an infinite number. Okay? There exists an infinite number of eigenvalues lambda n. of eigenvalues lambda n. Is it okay? And this is n equals to 1, 2, it goes on. Clear? So basically what it is saying is this. We really do not care what PQR is. Yes? You can always get an infinite sequence of eigenvalues lambda n. And the beautiful part is this. See, these lambdas, although they are real, it's not like a continuous spectrum, right? It's always a discrete spectrum. Lambda n, lambda 1, lambda 2, basically a countable number of values. Okay, lambda n. These eigenvalues can be arranged. So basically we can have a monotone sequence of eigenvalues, okay, arranged as a monotonically increasing sequence, okay. How is it? Lambda 1 less than lambda 2, and it goes on like this, right? Such that, so basically where is it going? Is it converging somewhere? The sequence, yes, it converges, it goes to infinity. Basically converges means in that sense it diverges, so it tends to infinity. Is it okay? And now another, moreover, a very important part. Okay, so basically first of all, what it is saying, you have an infinite sequence of eigenvalues. Yes, and of course if you have lambda s corresponding to a lambda s, you also have pn's, that's there. Now the thing is, what are the properties of lambda n? You can go on doing this lambda n. So basically you can actually arrange them in such a way that lambda n is a monotonically increasing sequence, right? And it goes to infinity as it tends to infinity. Okay. Moreover, you can say something about the zeros of lambda n. So what you can say is this. Moreover, eigenfunction phi n of x, okay, which is corresponding to lambda n. Yes. So basically let's say phi 1, lambda 1 is there, so corresponding to that phi 1 is there, right? So now the question is this, how many zeros will there be in an interval alpha beta, open interval alpha beta? So corresponding to lambda n's, okay, has exactly okay, n minus 1 zeros in alpha beta. It's a brilliant theorem, right? So you do realize what I'm trying to say. See, what I'm saying is this. Let's say lambda 1 is there. Corresponding to lambda 1, you have a eigen function phi 1. Now, how many zeros does phi 1 have? In this case, n is 1. n 1 minus 1, 0, 0. So there is no 0. So phi 1 is either positive or it is negative. It doesn't have any 0 anywhere in alpha beta. So it is not sign changing. Phi 1 is not sign changing. Is it okay? Right. What about phi 2? How many zeros does phi 2 have? So corresponding to lambda 2, you have phi 2, and phi 2 will have exactly 1 0. So there exists some x naught between alpha beta such that phi 2 of x naught is going to be 0. Is it okay? So brilliant theorem, right? And it's a very, very important theorem, yes, because it actually guarantees the existence of eigenvalues. Okay. So again, I am not proving the theorem, yes, and please, if you want, you can go through it using the Coddington book, not Levinson book. Yes. Okay. Now let's look at some examples of singular Sturm-Liouville boundary value problem. Okay. So regular Sturm-Liouville boundary value problem, we have some good ideas. Now let's look at the singular Sturm-Liouville boundary value problem. Okay. So singular Sturm-Liouville boundary value problem. By the way, the theorem which I just talked about, this last theorem, yeah, we are going to use this theorem. Yeah, it's not like I just gave you for a fun. This is very important in the sense that this will actually help you to help us to get through the next part of this video. Okay, but not this part. This is basically about singular boundary value problem. I just want to put some problem. This is basically a remark kind of thing you can think of. This is basically a remark. Okay. Okay. So this will actually tell you that if there is some difference here. Okay. So first of all, we will just look at some examples. Okay? Yeah. Now let's say that let us look at the problem y double prime plus lambda y equals to 0. Is it okay? That problem is there, and the data now is given to be y0 equals to 0. Yeah, and we do not have any data on the other part, but we know that mod yx is less than equal m. Is it okay? We don't have any other data. We just have mod yx is less than equal m, which is less than infinity. So basically, it is finite for all x in 0 infinity. Okay. Yes. So what you can do is this. So you have to do it yourself. Now you can check this part. Very important. You can check this part, that for each lambda between 0 and infinity. Okay. Sine root lambda x is a solution of the above problem. Okay. Now what do you think that implies? You see, what this is implying is this problem is definitely not a regular Sturm-Liouville boundary value problem, right? Okay. Now what did we just looked at this theorem. It said that for a regular boundary value problem, Sturm-Liouville boundary value problem, you will have a sequence of eigenvalues, right? Lambda 1, lambda 2, lambda 3, lambda n, which are increasing going to infinity. Yeah. But the thing is this, that the spectrum is the the set of eigenvalues, that is the spectrum is discrete. For a regular Sturm-Liouville boundary value problem, the spectrum is discrete. Is it okay? Now for a singular Sturm-Liouville boundary value problem, this theorem does not hold. Okay, so the spectrum is not exactly discrete. How do I know it? Because you see here, you can actually show that for each lambda between 0 and infinity, this is a continuous, this is an interval, right? 0 to infinity. So you can take any lambda you want, and you can get this function sine of root x lambda, root lambda x, and this is a solution. Yes, that is an eigenfunction. Yes, so eigenvalues are any value between 0 and infinity, and corresponding to that, eigenfunctions are given by sine of root lambda x. Yes, so the spectrum here, so spectrum may be, yes, you see, it is not like a guarantee that it will be continuous for a singular problem. It is may be continuous. But you see, in regular Sturm-Liouville boundary problem, it cannot be continuous. It has to be, how do I put it, discrete. Is it okay? Yes. Now the question, let me put it another question here. Yeah. Yeah. So can you, so question. So I want you to think about this question. Yes, I am not doing this part. So let's say that you look at this problem. Okay, let me write it this way. Consider 1 minus x square y double prime minus 2x y prime plus lambda y equals to 0. Is it okay? And the conditions which are given is, on the solutions are, limit x tends to minus 1 y of x is finite. Yes, and limit x tends to 1. You see, I have limit at 2 points, minus 1 and 1. So basically yx is finite. Okay. Now the thing is, I want you to find the eigenvalues of this problem. So find the eigenvalues, or maybe let me give it. The eigenvalues are given by lambda equals to n minus 1. So lambda n equals to n minus 1. N is in n. Okay, and the eigenfunctions phi n, let's say, phi n of x will be given by Pn minus 1 of x. These are the Legendre polynomial. Okay. Now, can you do this? Can you show this thing? So, can you please check this part? Check. Okay, so please try to do this part. Is it okay? So now the question is, so I hope this is clear. So basically what I am trying to say is this: whatever we have proved, the theorems and properties of this, these are all for regular Sturm Liouville boundary value problem. Okay. So what I am going to do is, in the next video, we are going to talk about a different kind of Sturm Liouville boundary value problem, which is called a periodic Sturm Liouville boundary value problem. Okay. So with this, I am going to end this video.